Yeah, my name is Giannis, and I'll be doing a very brief introduction to GPU programming. So for those who are either familiar or less familiar, what we're going to do here is basically a very sort of 101 introduction to CUDA. Okay, so those who have seen CUDA before, maybe this is not so useful. If you, though, have programmed before, something in C, some linear algebra operation or some simple kernel, which you haven't seen anything about GPU programming before, then maybe this is a bit useful for you to understand a bit how this goes. So there's a bit of an introductory part where I just explain a bit what the characteristics of a GPU is, what makes it different from like what you might be more used to like CPUs. And then there's a small example which we will go through step by step in order to understand a bit how we program GPUs. Okay? So that's just what I said. So the lecture part, so the lecture part involves a review of like the GPU architecture, and then I'll also give some details of the GPU part of the Cyclone supercomputer that you're already logged into. Then the hands-on parts will have one practical example, not plural, sorry, where we discuss a bit the difference between what you can expect from the GPU and what you can expect from CPU in terms of the same program. And what we will look at in particular, which is sort of the first thing you should understand when you program for GPUs, is exactly what the sort of memory layout is and why that's important. What I won't cover is some things that maybe you have heard about when talking about GPUs, which is shared memory and so-called warps. So these are things that I won't cover, but are equally important to understand GPU performance. So these are the assumptions I'm making about you, okay? About what you can sort of, how you can follow these slides so that you have some familiarity programming C or C++, okay? You know what a pointer is, how to allocate memory in C. I assume that you know this stuff. That you can edit files on the cluster remotely, right? Like, or you can use your VS Code to log into the cluster and edit files. But that you don't really know anything about programming GPUs. That's what I'm assuming. Okay. How much does this cover you? What's my coverage as far as this class is concerned? No? No. So you're not familiar with C? Okay. You have seen GPU programming before? No? Okay, that's good. You can edit the files on the server? Yes. Okay. Okay. We'll get there. Don't worry. Okay. So how you should I don't know. Maybe that's too low for everybody to see. How you should look at. So I advise you to have these slides up while we're talking. There's two ways. You can either get a PDF if you just go to this GitHub site, and then you navigate to. Do I need this? If you go to the GitHub site. Yes. So if I open this link, then you would go into this GPU programming folder. Okay. And you would go under slides, and then there's a PDF. Okay, but I would actually recommend that you get them from this website. They're the same slides, but they're so this would be just my, well, it's also written here, so it's just my slides.mysurname.net, and then it's EuroCC and the date in this sort of ISO format. Okay. Now, the reason I'm saying that this should be easier to copy paste things rather than reading from a PDF if you go here. Yeah, I don't have an SSL certificate on the site, but you can trust me, right? I'm not gonna... If you, sorry? No, you should, yeah. There should be a way to force it to go through. Okay, we good? Okay, if it's in a browser, the reason is that if it's in a browser, it's easier to follow links and to copy paste text. And also there'll be some scrollable text at some points, which you won't get in the PDF. Okay, so now I'll get right into it, right? So this is my very brief introduction to the GPU architecture. So this is a block diagram where on the left side, so you can think of this as a node, although a node usually has two of these. Are you having problem accessing the slides? You okay? You're not okay. So I was saying this is my sort of block diagram for a node where, okay, you can, this is actually taken from the system that you're going to use, which has, so it has two of these on each node, right? So I'm just looking on one side where you have a single socket CPU with some cores. In this case, there are 20 cores. And there's some, some memory, some RAM. And then you have a GPU, okay? Now a GPU is, if you want to contrast it a bit with so the way you should think of it is that whereas a CPU has, let's say, few sort of more heavy duty cores, a GPU has many sort of lighter cores, let's call them. Although what is called a GPU core is sort of fuzzy and depends on how you count. But in general, these boxes are also supposed to give you an idea of the different they're not to scale, but they give you the idea of the contrast between a CPU and a GPU. For example, a GPU has the GPU memory is usually smaller than what's available on the node in terms of CPU memory. Okay, so you have a smaller GPU memory, but this memory is high bandwidth. So if you have your data in GPU memory and you want to crunch the data using the GPU cores, then you go through this higher bandwidth bus here, which is usually, an order of magnitude or something like this, faster than the bandwidth by which you can access CPU memory from the CPU. The problem with the GPU, though, is that to get your data into this GPU memory, you first have to go through this, the regular RAM, through something which is lower bandwidth. In this case, this is like PCI Express 3, which is about 32 gigabytes. Maybe on another system, you might have PCI Express 4, but in any case, it'll still be much lower bandwidth than what you can access the GPU memory for. Okay, so you have some data that you want to analyze. Okay, if you're going to analyze them on the GPU, if you're going to do your operations to analyze this data on the GPU, then first you got to pay the cost of moving the data from the main memory of the CPU to the GPU memory over this bus. Okay, and if you can eat that cost, right, if it's still favorable, then you can get a benefit from the GPU, right? But if the computational task is so quick that basically you're spending all your time moving data in and out of the GPU, then the GPU will not be good for you. Okay, and another thing is that these GPU cores are optimized for parallel execution. So you can think of them, I don't know if you're familiar with this, but if you're familiar with how vectorization works on a CPU, like if you're familiar about how these SIMD, single instruction, multiple data operations happen on a CPU, where basically you have an array of data and you want to do the same operation on all the elements of the array. For example, you have two vectors and you want to add all the elements between them, right? You have a vector X and a vector Y, and you want to get a vector Z by doing, one by one the elements. So you can think of the GPU as having very long kind of sort of vector units, right? So it basically, these threads of the GPU, they work like they act on elements of a very long vector, right? So this is how you think of it. In other words, a GPU is very good at doing the same operation on a series of data, right? So if I have a vector which is like 1,000 elements, and I want to do the same operation in each element of this vector, this is ideal for that. If you want to do a lot of different operations on each element of the vector, like you want to, or you have a lot of control flow, like if statements, branching, etc., then the GPU is not sort of ideal for that. Or maybe we should say differently, to take advantage of the GPU, you should refactor your code in order to convert it to a code in which a lot of similar operations are done on many elements of an array. Okay, these are some numbers that, just to give you an idea, these are some numbers. They were already on the diagram there. So the GPUs that we're going to use are called V100 GPUs or Volta GPUs. This is basically 2 generations old. Okay, so the current version of GPU, or like these data center version GPUs, are from NVIDIA at least, are these so-called H100 GPUs. They haven't really been seen in real supercomputers, but they've been announced. at this point, and then the previous version are the Ampere GPUs, and this is one version back. Okay, so they're not that old, but they're not state of the art either. Okay? And these are some numbers of what you can expect from the different components. So memory bandwidth, as we said, is 900 gigabytes per second. So here I'm talking about the bandwidth at which you can read data from GPU memory to the GPU cores or write data back out. Okay. And the peak performance in double precision is something like 7 or 8 teraflops, where to contrast it with the CPU, these current CPUs peak performance is about 1 to 2 teraflops. I'm not exactly clear about the number, but yeah, somewhere out there. Okay, I'll come back to these numbers when we do our exercise. Okay, so the way we program the GPU is using this so-called offload model. This is not the only way to do it, but by far this is the most common way to program, to use a GPU. So the offload model basically means you run your program as you would regularly. So you run your program on a CPU, right? So the CPU starts the program main exactly as you would do normally. And then at some point in the code, you decide that you want to copy some data from CPU memory to GPU memory. Okay, so you basically call a kind of memcopy operation, which copies data from the CPU to the GPU. Okay, once the data is on the GPU, then you call so-called kernels, GPU kernels. These are functions that you have marked that you want them to be run on the GPU, right? And these functions can only see GPU memory. Okay, these functions that you have marked, the GPU functions, they can only see, they can only have access to GPU memory. That's why you have to go through this step first, which is copy data to GPU memory. Okay, you run your kernels, so you presumably you get some right, I have some problem rendering that math. So you run your GPU kernels, presumably they do some operation, they read the data, they write some data back. So when these kernels now finish, then probably you want to get some result out of the GPU. So then you call a new memcopy, which is copy data back from the GPU memory to the CPU memory, and now you can write them to a file, or I don't know, plot them, or whatever you would usually do with these things. Okay, so that's what I refer to there as this offload model. It's an offload model because you're offloading some work to the GPU, right? Whereas otherwise your program is running on the CPU. Okay, and these are just some terms. These are just some terms that we will be using in order to distinguish between the different memories that are available on the GPU. And the terminology that I use here is NVIDIA, is terminology used by NVIDIA because we're going to use NVIDIA GPUs. But also on AMD GPUs, probably you have the same kind of memory, just with different names. Okay, so there's global memory and so-called texture memory. And global memory is what I showed here, is what I called here the GPU memory. Okay, so that stuff, this orange box, these two orange boxes here correspond to this single orange box here. And I won't talk about this anymore in this lecture other than here, but GPU memory can be either read-only, which means this is read-only for the GPU threads, means that you can write data to there from the CPU, but these GPU cores can only read from that GPU memory, and that might be efficient sometimes. This is sometimes called texture memory or constant memory, okay? And so you can have either this constant memory or you have global memory, which is what you would think is the GPU cores can read and write this memory. No problem. Okay. And then there is this shared memory, which is memory that sits, I'm going back here, that sits closer to the GPU cores, okay? And this is, you can think of this as something like a cache, okay, for the GPUs. And although it is similar to a cache, it is, unlike a cache, you can sort of program it somehow as a user, okay? But this we will not cover today, we will not cover in this lecture, but maybe it's just useful to know that there's other kind of memory that one can use, which is faster than this memory here, okay? Okay. This fast memory, which is called shared memory, is quite small usually, and it's limited to about 96 kilobytes for a group of about 1,000 threads, okay? So, but as I said, we won't really be concerned, again, with this kind of memory here. Okay, now the work that you do on a GPU is usually you sort of break your work out into so-called blocks, okay? So a block, in this terminology, is just a group of GPU threads, okay? And usually what you do is you dispatch a set of blocks to run your kernels, and inside those blocks, there's some number of threads which sort of process the data or do the computations that you want to do within a block, okay? So you can choose the number of threads in each one of these blocks that you run, but there are limits. These limits are hardware limits, right? They depend on the architecture, but more or less any modern GPU that you use, by NVIDIA at least, this upper limit is 1,024 threads, okay? So you can go from 1 to 1,024. And if you want to use more than 1,024 threads, then you will just use more of these blocks, right? So the grouping is threads go into blocks, and then you decide how many blocks and how many threads per block you want to use. I won't spend too much time on those other numbers, but something to say about the execution order. Okay. Threads within the same block, you can synchronize, okay? So you have a block with, let's say, the maximum, which is 1,024 threads. So you can assume that when the block starts, then all these threads start together, and when the block finishes, then all these threads finish together, and you can also synchronize inside the block those threads. But you can make no assumption about when the first block will run and when the second block will run, etc. So the blocks are, between them, the blocks are completely asynchronous, okay? So they just run, you have no control over this. So maybe the GPU could decide to run one block after the other, or it could decide to run them all in parallel. Those are the two extreme cases that, as far as you are concerned as a programmer, are equally likely to happen, right? Let's say. But what you can assume is what you can consider sort of what you can control is what happens to the threads that run within a block, okay? So that's why this grouping is significant, right? You have the threads inside the block, which you can sort of synchronize and manage, you know, their order of execution. But then between blocks, you have no control about when one block runs and when another block runs, etc. Okay? So you make no assumption about the order by which blocks are executed. Okay. So the way we program basically the GPUs here for this specific case where we're using NVIDIA GPUs is we use this CUDA programming model, which is more or less a library. You can think of it as an API, okay? But it also has some features that are not very library like. So it also has some language features, language extensions to C, let's say, which are, yeah, so that's why you can't really call it a full API like library. So there's if you use CUDA, then usually you want to compile using the CUDA compiler, which is NVCC rather than CC or GCC. It provides you functions for transferring data to and from GPUs, right? So that's the library part. There's an API. With the CUDA library, you also get some high-level functionality, like you get some BLAS functions, for example, maybe some linear operation functions from the random number generators, etc. They're all packaged with this CUDA API. And although we'll talk about CUDA here, right, and how we program using NVIDIA's CUDA programming model, a lot of the concepts that we will see are generalizable also to other accelerator programming frameworks, and those are just some names I put there, like OpenCL, OpenAC, HIP. Okay, they all have, they basically all implement the same kind of functionality, but maybe with different names, okay, in different terms. Okay, so just to understand a bit before I go into the examples, in this CUDA parlance, host, wherever you see host, we mean the CPU, okay? So whatever runs on the CPU. Host memory is RAM, the host is the CPU. Device is the GPU. Device memory is the memory of the GPU. Device kernel is a function that will run on the GPU, etc. Okay. If you're familiar with C, which was one of my assumptions in the first slide, then you know that you need to allocate memory in C, right? In order to allocate a space for an array, you call this standard C function, which is called malloc. And there's a similar one that is provided by CUDA, and it's called CUDA malloc. And this reserves memory on the GPU memory. I'm going back now in the slides. So when you call CUDA malloc, you allocate memory here. And what this returns is a pointer to that memory. So this pointer is useless on the CPU, but you need to hold it on the CPU, okay? We will see that you hold a pointer on the CPU, which points to memory on the GPU. So you cannot really dereference it on the CPU, okay, on the host. But you need to carry it around on the CPU, okay. Okay, so you allocate memory like this. And you will see this regularly in these kind of GPU codes that people usually just, the variable names, they prepend them with this D underscore so that they know that this is a device pointer, right? I shouldn't dereference this pointer on the host because this memory is pointing to an address on the GPU. Okay, and then you deallocate it with free, right? Okay, transferring data to the GPU and from the GPU. It's the same function to transfer data to the GPU and from the GPU. The same function, it's called CUDA memcopy. Okay. But so you have two pointers. So this is the destination and this is the source. Okay. So my mnemonic to remember the order is to imagine that there's an equal sign between the first argument and the second argument, and then I can remember what the source is and what the destination is. Okay. Then it's the size and then the direction. Okay. And then this is where this terminology of what a host is and what a device is significant. So host to device means that you will copy from CPU memory to GPU memory, right? Device to host means that you're going the other direction. And then you should also interchange the two pointers so that on the left-hand side, you would have the host pointer, and on the right-hand side, you have the device pointer. Okay? So, when you do this operation, then this pointer here, this device pointer, as we say, should be an address which was returned by CUDA malloc, right? Which allocated memory on the GPU. And when you call this function, then this pointer here is the host pointer, so it should be a pointer to memory, which was returned by the regular malloc, right? Because this is on the CPU. Okay. Okay, and this is how you define functions that will run on the GPU. They're exactly the same as C functions, but you just decorate them with this attribute in front, underscore, underscore, global, underscore, okay? So this means compile this function also for the GPU. That tells the compiler basically that this should also be compiled to run on the GPU, okay? And how do you call this function? In order to tell the compiler that this is a function that I know I want to run on the GPU, you call it with this extra decoration here, okay? You would call it like, so if I were just to hide this part there, then that would look exactly like a regular C function call. But when you add these greater than and equal sign, greater than and less than signs there, or I don't know, chevrons, then that tells CUDA that this now, I want this to run on the GPU, okay? And what you specify here is the number of blocks and the number of threads per block. Those are just two numbers, right? They can be two numbers. You can just for example, you would just put 1024 here, and I don't know, 10 there. And that means it's going to run 10 blocks, and each one of these blocks will have 1024 threads running this kernel. Okay. Okay. I will say this, but this is not important for today at least, that this n block variable and this n thread variable, as I said, they can be just scalar numbers, right? Or they can be one of these dim3 types. This is a type that CUDA defines, which is just basically an array of 3 integers, right? You can define it like this. And this allows you for a 3-dimensional mapping of blocks and threads. So as I said, you don't really need to worry about this, but just know that this functionality is possible. Okay, and when this just allows one to not just have a scalar mapping of blocks and threads, but a higher dimensional one. I'll say a few things about this later, but it's not important for this. Okay. Now, when you're inside the CUDA kernel, okay, when you're inside, you have a way to know which thread is running this CUDA kernel, okay? You need like a thread ID. And in order to get the thread ID, you need 2 numbers. You need to know in which block am I running of these n blocks that you asked me to run on, and which thread within the block am I running, okay? So these are these 2 numbers here. Thread ID x.x tells you which thread this is running on within the block, okay? So if you asked for 10 blocks to run, and each block has 1024 threads, just as an example, then in each one of these 10 blocks, there will always be a thread which has, for example, thread ID x.x, which is 0, and thread ID x.x, which is 1, up to 1023, okay? Block ID x.x is the same, but for the block index, okay? So this here tells you in which one of these blocks are you running. And if you want to get the unique index, then you need to do a calculation like this, which basically says, first, tell me which thread I am in the block, and then add the block index times the number of threads in the block. right? In order to get a unique identifier for which thread index it is. As I said, this can be also three-dimensional. So you can also imagine that this is three-dimensional, right? So if you imagine that each green square here is a block, okay? And each orange dot is a thread inside the block, right? Then those are the dimensions for this case, right? So there's 16 threads horizontally. There's, what is it, 8 threads vertically. There's 4 blocks horizontally, and there's 3 blocks vertically, okay? So this is so there are 4 by 3 blocks, and then in each block, there's 16 by 8 threads, okay? And okay, so that block that I highlighted there, just as an example, that block that I highlighted there would have a block idx.y, all the threads, all, what is it, 16 by 8. What is that, 32, 64, 128, right? This should be 16 by 8 is 128. So all 128 threads in this block will have the same values for these two variables, because this is the block index. In the y direction, it's 1, right? 0, we start from 0, 0, 1, and block idx.x is 0, 1, 2. So all 128 threads will have these values here for block idx.y and block idx.x. And I'm just choosing that one there as an example, okay? And then if I just choose, for example, one thread, then this thread here, okay, will have thread idx.y 1, and thread idx.x 9, because we start from here, it's 0, 1, right? And it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You trust me, it's not. So, okay. Now, in this block, right, also this thread will have the same pair of these thread idx.x and thread idx.y, right? This thread here will have the same pair, but for this thread here, the block indexes will be different, right? Because this one will have a block idx.y of 0, right? And similarly, the threads inside here will have different pairs of that, but will have the same index up there, okay? So if you want a unique thread index, if you want one thread index to index the thread in this whole grid, then you have to do basically a calculation like the one I had in the previous slide, right? Where you go thread idx.x plus block idx.x times, and this block in.x is how many threads there are in the x direction of each block, right? And compute that. Okay. Okay. But for the single exercise that we will do in the next slides, the only thing we're going to do is use a one-dimensional. Basically, we will only have x. Okay, so this becomes a bit easier. But the two-dimensional or three-dimensional block subdivision becomes important sometimes. If you want to subdivide a physical problem which has 3 dimensions, right? And this can be a useful sort of utility to have available to you. Okay. So this is our exercise, just to see a bit how to use all this stuff. A very simple exercise, which is we basically have this very simple linear algebra operation. You have a vector y, you have a vector x, and you have a scalar variable a. And you want to scale x by a and add it to y and store it back in y. Okay? So this is the operation that we're going to do. And the length of this x and y is going to be large, right? It's going to basically fill up almost all of our memory. You already cloned this repository, hopefully, from the previous, exercise. So it should be there for you. Okay, but I'll let me just say a few bullet points here, and then we do it. Okay. So currently, the code that I'm providing to you does this whole thing on a CPU. So there's no GPU code in that program. Okay. There's only CPU code. So hopefully you can understand this code if you're familiar with C, but we'll go through it together anyway. So the idea is to step by step introduce the necessary code so that this is not done on the CPU anymore, but is done on the GPU. Okay, just we go step by step in order to include the different CUDA functions, etc., so that this operation is, when we run it, is run on the GPU. Okay, so in order to do this, we will cover these aspects. We will cover allocation of memory on the GPU. We will cover transferring from the CPU to the GPU and back, invoking CUDA kernels. Okay, and then we will discuss a bit about what is the optimal way to place threads and access the memory from the GPU. Okay. Okay. So what we want to do is look at this axp.cu program. Okay, CUDA programs usually come with a CU suffix. Excuse me just a second. Let me log into the cluster myself. Okay. Okay. Is it large enough? Yeah. All right. So here I am, and I should already have cloned this. What's it called? What's the is it there? What did I name it? Heroes is the training. Different training. All right, let me just clone it again then. Okay, so if I go now, EuroCC, yeah. So this is the intro to HPC, which was the last session. You guys want to CD into this one, and then into exercise. Okay, and there's a single .cu file here, and I will open it with Emacs. You're free to open it however way you wish. I'd need to tell Emacs that this is a C file so that I get some nice colors, yeah. And let's see what this is doing. So first I have some functions here that you shouldn't worry about. So this is just malloc wrapped in error checking. This is just a timing function. This is the CPU version of AX plus Y, okay, which has some OpenMP implemented above. So this is what we want to do, but on the GPU now. But now it's done on the CPU. Okay. So this is a function that takes two arrays X and Y and a scalar A. The size of the array is N. And so you just have a very simple loop that does Y equals AX plus Y for each element of the array I. Okay.
Okay, so what I'm doing here is, I'll explain this a bit. It needs to be explained. So first I'm allocating 2 arrays X and 2 arrays Y. And I'm filling both X and Y with the same numbers, both versions of X and both arrays, which I call Y, with the same numbers. And, oops, I want to open this up a bit. Okay, so it fills the screen. And let me show you what's going on here. So I call this section A, okay? You can pay attention a bit to the screen. Maybe it's easier if I explain this. So in this part A, then this is basically where all the computation is happening. So I'm calling AX plus Y on the X0 and Y0 arrays. And then I'm printing some performance here. Okay, something about the performance. And then I'm doing the same thing here in this section B, further down. It's doing exactly the same thing, but with Y1 and X1. Okay, so it's exactly the same thing. And the reason I'm doing it like this is because I want to have 2 copies, so that what I'm going to do is make this run on the GPU, the second part. I'm going to keep the first part to compare with. Okay, I'm just going to keep this A part. Okay, so this I will leave untouched. But this part here, I will move to the GPU, okay? So that I have a version that works on the CPU, and then I have another one that works on the GPU. Right, and because I want to be careful, I will, at the end, compare the 2 Y results between them. So I'll compute their difference, their normalized difference, and if it's smaller than the machine precision, if it's bigger, if this difference is bigger than the machine precision, then I will be worried that maybe I made a mistake on the GPU code, okay? So I just want to check that the CPU code and the GPU and what will be the GPU code here give me the same results, okay? That's what I'm doing. All right. Very good. Questions up to here? Okay. Okay, let's see. So what we can do is, so this is all explained here. Okay, so in order, just to make sure that we're all using the same compiler and the same modules, etc. So we will compile this code as it is, with no GPU stuff, right? Just to make sure that we can actually compile it. So modulo GOMPI, just to make sure we're all using the same version of the C compiler. Modulo CUDA, you can just copy and paste this. And then this is the compile command that will compile our code with the NVCC compiler, even though there's no GPU code at this moment in this C file, okay? Okay. So there's my executable. Okay, maybe it's easy to read if it's higher up. That's my executable. And okay, I might be over complicating things here, but this is just to make sure that I'm running it on the right number of cores and etc. Don't worry too much about these commands. This is just to make sure that the CPU part is optimal. Let's see if this actually works with the reservation. I'm wondering myself if this is active still. Okay, and what I'm specifying here is the executable AX plus Y, And this is the length of the X and the Y vectors, okay? So this is going to be 1024 times 1024 times 64. So basically 64 million elements is the length of the X and the Y. This is probably booting some idle node, and that's why it's taking too long. But eventually this should run. Yeah, I see several of you are also waiting for the nodes to wake up. This will only take long this first time, okay? Okay, but in any case, you should get something like this. Oops, oh, no, wrong browser. Let me see. Yeah, you should get something like this, where you have two lines, which is this A part and this B part, which are both running on the CPU, right? So for now, and you should get a diff, which is exactly 0. This is the difference of the two results, which should be 0 because they're both running on the CPU. Okay. Did you register? Did you register for this lesson? It's still, I guess it's still booting the nodes. Has anybody's job gone through? Okay. Okay. It's been 5 minutes already, yeah. By the way, is somebody checking the Zoom chat? Okay. Okay, finally. Right, so 90 to 100 gigabytes per second is the number that we want to look at here. And just to remind you, this is all running on the CPU. So we're basically going through this memory bandwidth here, right? So this is basically what we're measuring. The peak is 130, and we're getting something between 90 and 100, right? Roughly. So that sort of makes sense. So the question is, if we go to the GPU now and we do the same thing and we measure the same timing, will we get something close to 900 gigabytes per second rather than, you know, sort of 100, right? That's sort of our goal, not only to run it on the GPU, but also take advantage of the higher memory bandwidth that is available to us, presumably, on the GPU. Okay, so let me roll back to where I was, and this is where I was. Okay. Right, so this is what we need to do. I mean, we will go through this together, but what we need to do in order to get this part to the second part to run on the GPU is, well, we need to do some things outside of main and some things inside of the main program. This is how I decided to split this up. So let's look at the edits we need to do inside of main, outside of main. We need to add a header file. Okay, that seems trivial. Okay. The second thing we need to do is we need to add a kernel with this declaration global that will do this AXP operation, AX plus Y operation, because we needed to have a kernel that will be marked to run on the GPU, okay? And then the other thing that we need to do outside of this AX plus Y is add functions similar to the ones that we use to allocate the arrays on the CPU. We will add functions that do the same, but that use this CUDA malloc rather than the regular malloc in order to allocate the memory on the GPU. Okay. And then there are some things that we need to do inside the main program. And inside the main program, we need to, of course, allocate the arrays, which will now be kept on GPU memory. We need to copy the data that is the input from CPU memory to GPU memory using CUDA memcopy. Then we need to call the GPU kernel, and then we need to copy back the result. If we don't copy back the result, then our program will say that these two Y arrays that you've computed are different, right? Because at the end, as I said, we do a comparison between the two Y, the Y0 and the Y1. Okay, so that's basically the order in which I will do these edits. First, the edits outside of main, and then the edits inside of main. And feel free to copy paste also from the slides, because I definitely will be doing that. So let's go back to my AX plus Y. Again, I will remind Emacs that this is a C file so that it gives me nice highlighting. So again, I'm just following these bullet points here. The first one is add the CUDA runtime header file. CUDA runtime. Okay. Okay, the second one is add the GPU kernel, naming it GPU AX plus Y. So for now, all I'm going to do is basically copy the CPU kernel, copy it and name it GPU AXP, and put this global attribute in front, okay? This is, of course, not going to be the end of the story, but that's what I'm going to do for now. Okay. The line number is this here. Okay. This is where I am. No. How do I? line number mode. No, that's not it. Anyway, I'm going to copy paste this. Okay, I'm going to change this comment here so that I don't on the GPU using, I don't know, CUDA. Always update your comments, guys. So this is GPU underscore AXP. And of course, this pragma OMP is nonsense on the GPU. So I'm just going to, and global. Yeah. Clear? Okay. Okay. 3, we want to basically, we have this, well, I didn't talk about this maybe sufficiently, but here is how I allocate arrays. I'm just basically wrapping this malloc function. So this is a standard function in C, malloc. It's how you allocate arrays in C. I've just wrapped it around my own function so that I can check if there has been an error, so that my program doesn't continue if the system malloc gives me an error. That's all this does. Okay. And I'm going to add this function here, which does the same, but does it with CUDA malloc. Right. So this one uses CUDA malloc there, which allocates memory on the GPU. Okay. Copy paste this function. Doesn't matter where exactly you put it, as long as it's before main. So this is the CPU function, right? This runs on the CPU and will allocate memory on the GPU and return to me a GPU pointer, a pointer that points to memory on the device, right? This is what this does. I can wait for people to catch up. Just tell me if you want me to go slower. Even slower. This one? You just add this somewhere before main. I mean, I put it so I put it before the other AXP. But you don't have to put it there as long as it's before main. Sorry? In what? Yeah, that's fine. Okay, so those are all the edits that we did in terms of doing things outside of the main program. And now we will go into the main program. And the first thing that we want to do is allocate the memory that will hold the X array and the Y array on the GPU, right? So we want to allocate memory on the GPU and return the device pointers, the pointers that will point to GPU memory. So these 3 dots here just mean you do this, you add these 2 lines at the beginning of this B section, right? And you add these 2 lines at the end of this. So let me show you what I mean. So I will go down, how am I going to make this? I hope you can still see everything, but I go down to the main program. Here's where the main program starts. And as we said before, then this has this segment, this A segment here, which is doing the calculation on the GPU, on the CPU, sorry. We won't touch this. We will go down here where it says B. And okay, and before we do anything, we need to allocate the GPU memory. So here we will put these 2 lines, okay, like this. So this will allocate memory on the GPU. And we just, because we're very careful programmers, we will remember now to deallocate these arrays here at the end of this block with CUDA free. Okay. So I added these 2 lines and these 2 lines. Okay, those are the 4 lines I added so far to this block of code, which I call B inside, which, you know, B, I mean capital B. Yeah? Here? Okay. Okay, who's going to remind me what we need to do now? What's the next step? Silence. Sorry? The calculation. No, we have to do something before that. Yes, but we need to do something before that. Pandeli. Transfer data. It's the next slide, guys. You can just go next slide and pretend like you. Yeah. So but that's not what you did, Bandeli. You didn't go to the next slide. So so here we are. So now we need to copy to the GPU the 2 arrays. So we've allocated the memory on the GPU, but this memory is uninitialized on the GPU, right? So now you want to copy X and Y from the CPU to the GPU, okay? And we do this with this there. Okay. We allocated the data, but it's still uninitialized. Uninitialized. So it had, well, it has zeros in it, basically. We just allocated the memory. Yes. Is this mem copy? Yes. Okay. Because this X and this Y has been set with random numbers on the host, on the CPU, right? No, because the program started on the CPU. So here at the top, right? We allocate X and Y, and we fill in X and Y with these random numbers. But so far, this is all on the CPU, okay? Okay, this runs on the CPU, we said. And then here, now we've allocated these arrays on the GPU, these two arrays, but they don't have any data in them. We just allocated them. So now we're going to copy the data. Now is when we do this, what I talked about at the beginning, about moving the data from this memory over to the GPU memory. Okay? Yes, we push it. Well, we push it through the doors. Yeah. Okay. So you can copy that and put it here. Okay, and just remember that this is, this is copy. Here it says host to device, right? So we're going from CPU to GPU is the mem copy that we're doing here. And we're copying X1 to this DX, which is the memory that we just allocated on the GPU. And we're doing Y to DY, which is also memory we just allocated on the GPU. Yeah. Okay. Should I wait a bit? Okay. All right. And now we call our CUDA kernel. So now we come to what you asked me to do before, which is call the kernel. This AXPY is the name of the kernel, is the name of the CPU function. So we need to, we decided to name the other one GPU underscore AXPY. This is just our choice. We decided to name it GPU. You don't have to name it GPU. What you do have to do is put this attribute global in front. So that tells it that it's going to be a GPU function. And for now, we're just going to run one thread, one block, one thread. Okay. Again, this is not ideal. But we do this for now. Okay. One block, one thread per block. And okay, this is probably the biggest gotcha, right? So the pointers that we pass to the GPU kernel have to be pointers to memory on the GPU memory. So here we need to pass dx and dy. Okay. Yeah. Very good. We're almost done. What's left? I told you how to cheat. So you should feel free to cheat. What's left? Come on. Thank you. Yes, very good. Copy Y back from the GPU. This is this line here. And we do this. We do this here after we have called the AXPY kernel. All right, so there's one last thing which I didn't write in the bullet points is that this thing here is a bit misleading now because we're not using the CPU. So you can just delete this and just write GPU here. Okay, just turn it to something like this. And remember to delete the NTH. So this should turn into something like this. So the 3 dots here, I just mean, that there's something here that I'm not writing in the slides. Don't actually put 3 dots, right? And you can also remove the, okay, you don't need to do that. I think we're ready to roll. So we need to recompile. and rerun this. Okay, so I can arrow up to the nbcc command that I used last time. And then arrow up to the srun command. Okay. So I deliberately tricked you into falling into something here, which I will discuss as soon as, so if everybody's more or less here, then I can discuss this. So, okay, so we run on the GPU and we get a reasonable number for this difference, right? This is more or less machine precision, 10 to the minus 15. But this bandwidth here is 23,000 gigabytes per second, which is completely implausible, right? There's no way. I mean, we said the peak bandwidth is 900 gigabytes. So what did we do? So what we did was, and as I said, I sort of deliberately sort of did it this way so that I can make a point out of this, is, oops, mode, is that so what I should note is that the GPU kernels, okay, they run asynchronously on the GPU. So that means that what you are doing here is you're asking the GPU to run this kernel, and the program is returning immediately back to main. Okay, so this timer here that I've wrapped this kernel around is basically just timing the split second it takes to call the function, but it doesn't wait for the CUDA kernel to complete to return. Okay, so the CUDA kernels, they run asynchronously. This is a feature, right? You might want the GPU to run doing something, and you might want to use the main program, the CPU, to do something else. So that's why these GPU kernels don't wait the way that you call them. Oops, what did I do? Is you're not waiting here for the kernel to finish before you come out and measure the timing again. Okay. So that's what's going on there, and what you can do in order to make sure that the timing that you're measuring is indeed the time it takes for the kernel to complete is make sure that you synchronize the device before you call the stopwatch. So this CUDA device synchronize waits for all kernels to finish before continuing. Okay, so this synchronizes the CPU code with the GPU code. Okay, if I don't put that, I repeat, if I don't put that, then the GPU will keep running and the CPU will call this stopwatch function, and the timing that you'll get is not the timing it takes to complete the GPU kernel, it's just the timing it takes to call the kernel, which is nothing, right? Okay. Okay. So if you add that, then now we should recompile. And we should run. Okay. So now this timing looks more feasible, let's say, okay? It's not 20,000 gigabytes per second, but it's also extremely small. And it's no surprise that this is extremely small because we have been only using one GPU thread and one block, right? And all the power of the GPU comes from using many threads in parallel. Okay. Was there a question? No. Okay. Sorry. Okay. So what are we going to do now? Well, we're going to use more threads. Okay. So let's use 512 threads, okay, and one block. So one block, 512 threads. So the way to do that is we go back to our code. And this is where we determine the number of blocks and the number of threads per block, right? So let's just say we do 512 threads and one block. Okay, one block, 512 threads. Now, we have not taken care of the GPU kernel. So the GPU kernel here, no, the GPU kernel is this one. Okay, so this goes from 0 to n, right? Goes I equals 0 to n, and n is the whole extent of the array. If we run this with 512 threads, then all we will achieve is that these 512 threads will all do the same thing, which is not what we want to do. Okay, so now we're going to run this with 512 threads, and what we want is to distribute this n up there. We want to distribute it to the 512 threads, right? We want to make sure that they're not all doing the same thing, and that the first thread, for example, is doing the first n over 512 elements. The second thread is doing the second 512 n over 512 elements, etc. So one way to do that, there's no unique way to distribute it, but one way to do that is shown here. Okay, so remember that we can get the number of threads by using we can get the thread index, I should say, the thread index, by using this thread idx.x. Okay, this gives us a unique number, which is the index of the thread within the block. So if we're running with 512 threads per block, then this number would be 0 for the first thread, 1 for the second thread, up to 511 for the last one. Okay, this is what they started. The block dim is just the number of threads inside the block, right? So this number will be 512 for all of the threads. It's just the size. Right? So it's the number of threads that are running in this block. And so if I know the block dim and the thread index, then I know how to distribute my for loop between the threads, right? So let's do that. Okay, so I repeat, this I thread is just the index of the thread. So for the first thread, it's 0. For the second thread, it's 1. For the last thread, it's 511. This n threads is the number 512 for all the threads, right? It's just the size. And then this number here, LT, is just the number of elements that each thread should compute. So we have n total number of elements. We have n threads. So the number of elements that correspond to each thread is just n over nthr. So if I were more careful here, I would check that this is divisible, that n is divisible by the number of threads, and take care of doing whatever I need to do if it's not divisible. But okay, you can imagine that code, I guess, if you want to implement it like this. Okay, now the for loop there is still wrong because it's still going from 0 to n. Okay, I have to change it, and okay, I'll just write it. And then if you have any questions about why it is like this, so this is I thread times LT. I smaller than I thread plus 1 times LT, I plus plus. Okay, right. So the first thread will have an index of 0. So the first thread will have the value ithr will be 0. And so for the first thread, this loop will be from 0 until LT. Okay, so it will do the first LT elements of the array.
For the second thread, this ITHR will be 1. Okay, that will be the thread index of the second thread. And so the second thread will go from LT to 2 times LT. Okay, and LT we've already defined as being the number of elements that each thread should compute. Okay, so when we're done, the complete array should have been computed, right, from 0 to n minus 1. Okay, let's compile that and run it again and see what we get. So we're interested in seeing whether this gets faster. And it does get faster. We get about 4 gigabytes per second, where before we got 0.2. So this is 20 times faster, not 512 times faster, but 20 times faster. Okay. I keep coming back to this number. The peak bandwidth is 900 gigabytes per second, right? So this is still very far away from the peak bandwidth. So it's better than what it was before, but it seems like we have some room for improvement. So to talk about that, so now it's important to talk a bit about the memory model. And although I won't explain the details about, you know, the memory layout of the GPU, sort of the key takeaway from this part of this hands-on exercise, or basically from the whole hands-on exercise, is that what you want to do on the GPU is not this. This is what we're doing currently. So thread 0 is taking the first element of the array, the second element of the array, the third element of the array, up to I guess the LT minus 1 element of the array, right? So the first element, the first thread is taking the first chunk of the array. The second thread is taking the second chunk of it. Okay. This is suboptimal. The GPU is designed to do vector operations, right? And so what you want to do is exactly the transpose of this. You want that the first thread takes the first element of the array, the second thread takes the second element of the array, the third thread takes the third element of the array, and so on until you exhaust your threads and then start over. Okay, so you want to transpose this. Basically, I'm just talking about, you know, you want to change this so that you the sort of transpose operation. This is sort of the opposite of what we do when we use, for example, OpenMP to parallelize you know, array operations, where usually you have one core take a chunk of the data and then another core the other chunk of the data. So the GPU memory model is inefficient when you do that. What you want to do is you want to interleave the threads so that they take consecutive elements of the array. Okay. So one way to do that, and again, this is not unique, but one way to do that is to turn the loop to jump by n thread iterations each time, like I did here. And if you do that, then you should get something which is improved, like here. So let me do it also in my code. Oops. Let's see you. Okay, so I don't want to do this anymore. I want to do this. Okay, so let's see what this is doing. So all the threads start with I equals 0, right? All the threads, but they're adding their thread index, they're adding their thread index to the element that they're reading. Okay, so
thread 0 will take element 0, thread 1 will take element 1, thread 2 will take element 2, and so on. And when you run out of threads, then you increment this by n thread. So then in the next iteration, thread 0 will take element n thread. Thread 1 will take element n thread plus 1. Thread 2 will take element n thread plus 2. And I'm basically implementing this schedule for parallelizing the loop rather than the one we had before, which was this schedule. Okay, compile and run. And now you should get something closer to what I have here on the slide, which is 12 gigabytes per second. This is still low, but now the next step that is going to be the last step, which is basically now use also more blocks. Okay, so right now, if you remember what I asked you to do was use one block, 512 threads per block, right? Now we're going to use more blocks. And actually, what we're going to do is use as many blocks as we need to completely pad the n elements with blocks, all right? So there's no reason to do any loop in the kernel anymore. So watch this. So if I do, let's put n threads here equals 512, just so that we have a variable. And so now we put here n threads, and here we put n over n threads, okay? So there are as many blocks and as many threads per block as there are elements in the array. So basically we have one GPU thread corresponding to each element of the array that we want to operate on, which means that we can completely, as I said before, eliminate the loop that you need inside the GPU kernel. So what does that mean? That means that you can do something like this, where you compute the global thread index, and then that global thread index is a number that goes from 0 to n minus 1. Okay, so it involves the thread index, but it also involves the block index, right? So it's a number that goes from 0 to n minus 1. You have one thread for each element of the array. And so now you don't need a loop anymore. The loop is implied, is sort of built into the distribution of threads over the array. And this is very common to do for GPU kernels, right? So you don't have, by the way, you don't have n hardware threads on the GPU, right? The scheduler will take care of scheduling the different blocks at different times. So don't think that you will have 64 million GPU threads running in parallel, even though it looks like this is what you're doing, right? The GPU hardware is sort of scheduling everything in an optimal way, which is completely opaque to you, right? But it looks as if you're really allocating 64 billion threads in parallel. Okay. And VCC. And now if we run this, okay, so now you get 730 gigabytes, and now we are very close to this 900 gigabytes per second that I told you is the peak bandwidth of the GPU, okay? So you can do a bit better than this if you optimize the number of threads and the number of threads per block, right? So maybe you can tweak that a bit, but the best you can do is probably 750 or 780, which is already something like 80% of the peak bandwidth, which is more or less what you can expect to get with just the regular sort of regular C code like this that we're using. Okay, so that was basically what I wanted to say. So the take-home messages is, well, if you've never seen GPU programming, then hopefully you've gotten some high-level understanding of the sort of steps that you need to do. that you need to allocate data on the GPU, copy memory to the GPU and back, etc. And hopefully you've also gotten some idea of how to think of, the thread placement inside of the GPU. We didn't talk about a lot of things. So we didn't talk about what happens if you want to share memory between the different GPU threads. So this we didn't cover at all. How to use like this shared memory, which is like a cache. But hopefully now you can read some CUDA code and look at these weird signs and understand that this is something that you've seen before. And yeah, so if you want to do this offline and have any questions, then feel free to ask me, to write me a mail, or I don't know, however else you want to ask me, find me, just I guess ask Anneliese. Yeah, I'd be happy to answer.
Thank you very much, Yanni. Are there any questions?